So, implicit differentiation. You may ask, what is implicit differentiation? Why do we have to have it? We already have differentiation. Well, what we've done so far is explicit differentiation, where our equation is y equals something in terms of x. That's explicit, where it's clear y is defined explicitly in terms of x. Well, implicit you could think of as hidden. So x and y are mixed in together, and it may be an equation that you can't easily solve for y, so that y is explicitly defined in terms of x. So implicit differentiation is when we get an equation that's not y equals something in terms of x. So to introduce it to you, I'm going to use this graph, and this graph has a special name. It's called a folium. And the reason it gets a special name is because it was discovered by a special man, Descartes. And this graph, this curve, is extremely old. It originated in 1638. And what Descartes discovered was this graph, a folium, could be defined by three different functions. You have one here, the blue one, the pink one, and the green one. And he discovered the equation for this curve, x cubed plus y cubed minus 9xy equals 0. And the reason why this is a good example to introduce implicit differentiation is because no matter what I do, I cannot solve this function just for y. I can't get y equals something in terms of x. It just won't work. So for whatever reason, let's say we still need to find the derivative. We still want to know the slope right here at this point. And as you can see, it's not a function, which is why I can't solve for it explicitly. So how do I find the derivative? Well, I'll show you. What I do is I go ahead and take the derivative of each variable, but I have to remember my differentials. In other words, the derivative of x cubed is 3x, and that's the derivative of x with respect to x, so dx over dx. And then y cubed would be 3x squared. And then y cubed would be 3y squared, but I just took the derivative of y with respect to x, so I have to include my dy over dx. And then 9xy is a product, so I need to use the product rule. Just slide this over here. So the first half is, I'm going to say, negative 9x. Second half is y. So using the product rule, take the derivative of the 9x, and you get 9. And then plus, we're going to take the derivative of y now. Well, derivative of y is 1, so we're just left with dy over dx equals 0, because the derivative of 0 is 0. Now, one thing that can happen here is that when I have dx over dx, it's just 1. So those can go away. And then I'm left with, let's see, I have a 3x squared plus 3y squared dy over dx minus 9y minus 9x dy over dx equals 0. And then I need to solve for dy over dx, because no matter what, let's get our derivative explicitly. So dy over dx on one side, and then everything else on the other. So let's see, I have a 3x squared here and a negative 9y here, so I'm going to move them to the other side. And that leaves me with 3y squared times dy over dx minus 9x dy over dx equals, and then I'm going to subtract 3x squared from both sides, add 9y to both sides, and I'm left with that. Now, what I can do from here is I can first move my stuff around so I have enough space. I am going to factor out a dy over dx from both of these terms. And once I do that, I'll be left with dy over dx times 3y squared minus 9x. It'll look like this. That was Mr. Joyce. Thank you, Mr. Joyce. So then I can divide both sides by what's in parentheses here and get dy over dx completely by itself. And inevitably I have run out of space again, so I'm going to shrink this down, move it. Alright, so then let's see, dy over dx equals negative 3x squared plus 9y all over 3y squared minus 9x. And that would be my derivative. Define explicitly. We have dy over dx on one side, and then my derivative on the other. And that was implicit differentiation, where x and y are mixed in together.